Okay, we're not doing anything new today. We're just going to practice linear approximation again. First thing we're going to do, we're going to try to find the equation of the tangent line. So we need a point. You have a point right here. We need a slope. Well, we have a way of finding the slope. So for us, when x is 7, we could plug the 7 into the slope formula, and that would give us 10 over 2, and so that's 5. So our slope is 5, and our point is going to be 7, 11. Now we can do the equation of a line. The equation of a line is going to be y minus 11 equals m, and then x minus 7. I'm going to add 11 to both sides, and that's it. As long as x is near 7, our function will be approximately equal to this line. Now we can use this tangent line to approximate the function when x is 7.1. We just need to plug in 7.1. Okay, if we plug in 7.1, we would get this. And 7.1 minus 7 is just 0.1. 0.1 is the same as 1/10. This is 5 over 10, and so that's the same thing as 1/2. And we can just leave our answer like this, that's fine. Okay, we have 6 examples. This is our second example. We're going to use linear approximation to approximate the value of sine of 61 degrees. You'll notice we'll start by calling our function sine of x. We've got to choose a point. And we need an x value that's close to 61 degrees that we know. But we know sine of 60 degrees, so we're going to let x equal 60. And if we plug in 60 degrees into our function, we get sine of 60 degrees, which is root 3 over 2. So now we have our point. In order to do the equation of a line, we need a point, we need a slope. To get the slope, we have to do the derivative of sine, and that would give us cosine. We're going to plug our x value into cosine. So we're plugging 60 degrees into cosine. Cosine of 60 equals 1/2. That's our slope. And now we can plug it into the equation of a line. The x goes right here, so that's 60 degrees. The y is root 3 over 2, goes right here, root 3 over 2. And the slope is 1/2. The slope goes right here. We can solve it for y. We're going to have to add root 3 over 2 to both sides. Now, this is the equation of our tangent line. But as long as x is near 60 degrees, we can say that our function is approximately equal to this tangent line. We can plug in 61 degrees. And that's because 61 degrees is close to 60 degrees. Sometimes I call that number the weird number, and it's the number that you plug in at the end. So if we plug in 61 degrees, we're going to end up with 1 degree inside here. Now I don't want to leave it as 1 degree, because then I'll have this thing in terms of degrees, and then this one's kind of in terms of radians. So I'm going to change 1 degree into radians, and you can do that if you multiply by pi over 180. Then the degrees will cancel, and you end up with pi over 360 plus root 3 over 2. Now that's our estimate, but let's see how close our estimate really is to the real final answer. If you use a calculator and type in sine of 61 degrees, this is what you'll get for your answer. Now let's compare that with the estimate that we got. If you plug that in a calculator, this is what you would get for your answer. Now I want you to notice that our estimate was accurate up to 3 decimal places. And we didn't even use a calculator to get that answer. This is what we got, and we got this without a calculator. And again, it was accurate up to 3 decimals of accuracy. That's a pretty good estimate. Okay, this is example number 3 out of 6. We want to use linear approximation to approximate the value of the third root of 7.9. So our function is going to be the third root of x. And we're going to choose an x value of 8, because 8 is close to 7.9, and we know the third root of 8. The third root of 8 is just going to be 2, so that gives us a point when x is 8, y is 2. Okay, we're trying to do linear approximation, so we need to do the equation of a line. We have a point, so now we just need a slope. Remember, the slope is just the derivative. Okay, again, our function is the third root of x, so you can rewrite that as x to the power of 1/3. So when we do the derivative, the 1/3 comes down, and the new power is 1 less. So that'd be like 1/3 minus 3/3, and that's how we're getting negative 2/3. Now a power of negative 2/3 on the top would become a power of positive 2/3 if you move it to the bottom. Now this is kind of like x squared, and the third is really the third root. Now the squared could be on the outside or it could be on the inside. I prefer to leave it on the outside because it's easier to do the third root first. The third root of 8 is just going to be a 2, it makes it smaller, and then you just have 2 squared, which is 4, so the bottom is 3 times 4. So that's how we're getting 1/12 for our slope. Okay, now we can do the equation of our tangent line, because we have a point and we just figured out the slope. The slope is 1/12. Okay, let's go ahead and plug in our point. 8 for x and 2 for y. So 8 is going to go here, and 2 is going to go right here. Remember the slope was 1/12, so that's going to go for the m. Then we need to add 2 to both sides to cancel the minus 2. But I'm going to write 2 as 24/12, and that way I can combine it with the minus 8/12. You'll notice we had to multiply the 1/12 times each piece, and that's how I'm getting minus 8/12. Okay, I'm going to combine these two fractions. Okay, final answer for our tangent line, 1/12 x plus 4/3. And that's because this is going to give us 16/12, but 16 is 4 times 4, and 12 is 3 times 4. So you can see we can cancel the 4's, and we're left with 4/3. So that's how we're getting the 4/3. Okay, so what we're saying is our function, which is the third root of x, is approximately equal to this tangent line as long as x is close to 8. Now the x that we want to use is 7.9. That's what I'm calling my weird number. So we can plug in 7.9. And so the third root of 7.9 is equal to f of 7.9. But that's approximately equal to plugging in 7.9 into the equation of our tangent line. Our tangent line approximation gave us 1.9916. The exact value that comes from the graphing calculator is also 1.9916. So you can see we're accurate up to 4 decimals in this situation, and we did that without a graphing calculator. So the answer that we got right here was solved without a graphing calculator, and look at how accurate we got. Okay, we're going to do number 4 out of 6 problems. Okay, we want to go ahead and approximate this value here when h is near 0. So that's going to be kind of like our x. If you don't like using h's, switch it to x right now. You can say let h equal x. And then you can just use x's instead of h. And it would be y of x equals 2 to the k plus x. Now here k is meant to be a constant. Just treat it like a number 5 or something like that. Now the first thing we have to do is figure out what our function is. So here's going to be our function right here. And remember that h is kind of like an x. So that's going to be your x. So instead of y of x is y of h. Now we need a point. What x value are we going to choose? We need h to be really close to 0. So then let's just choose 0 for h. Now if you plug in 0, you're going to get 2 to the k plus 0. And so that's just going to be 2 to the k. And now we have a point. Remember, we're trying to do the equation of a line. We have a point, so now we just need a slope. Okay, if you remember the derivative for 2 to the x is going to be 2 to the x and then ln of 2. Now what we have is we have like an x plus k. That's just a constant. So our derivative is going to be 2 to the x plus k times ln of 2. But then we have to do the derivative of x plus k. But that's just going to be a 1. Now remember, instead of an x, we have an h. So we're doing this kind of a derivative, d dh. So we're doing a derivative where h is supposed to be the variable. Okay, this is the derivative for any value of h. Our value of h is 0. So we need to plug a 0 for the h. And that'll tell us the slope when h is 0. Plug a 0 right here, we just get 2 to the k times ln of 2. And that's going to be our slope. Now that is a weird value, but it's still just a constant. So we're going to plug that for the slope. So we're plugging it right here. And then our point is going to be 0 for x. So we're going to put the 0 right here. And 2 to the k is going to be the y. Now h minus 0 is going to be just an h. We're going to have to add 2 to the k to both sides. So you get a plus 2 to the k over here. And that's it. So that means our function, which was 2 to the power of k plus h, is approximately equal to our tangent line right here. Remember, the slope of our tangent line is this weird constant right here. And this is kind of like an x, but we're using h. And this is our y-intercept right here, 2 to the k. So our constants were really weird. And even our x value was kind of weird. It was an h instead of an x. So this is a pretty tricky example. This is probably the hardest one that we do. Okay, this is example number 5 out of 6. On this example, you can see they're asking us to approximate ln of x plus 1 when x is 2. So if you just plug the 2 in, you can see that they're asking you to approximate ln of 2 plus 1 or ln of 3. Now, when they say approximate ln of 3, in calculus, what they want you to do is they want you to use tangent line approximation to approximate ln of 3. So that means our function is going to be ln of x. And we need to find an x value that we know that's really close to 3. Some of the easy ln's that we know is we know ln of 1, that's 0. We know ln of e, that's equal to 1. Now e is about 2.7, so that's pretty close to 3. I think that would be a good x value. So we're going to choose an x value of e. When we plug it into ln of x, we get ln of e, which is 1. So now we have our point. So we have our function is going to be ln of x. Our point is going to be e comma 1. And then for our slope, we're going to have to do the derivative. The derivative of ln of x is just 1 over x. But that's the slope for any value of x. We need the slope when x is e. So we're going to trade the x for e, and we get a slope of 1 over e. Okay, now that we have the point and we have the slope, let's go ahead and do our equation of our tangent line. We're going to say y minus 1 equals m, and then x minus e. Okay, so our slope was plugged in right here for the m. Our x value was e, and our y value was 1. We can add 1 to both sides. Now this is y of x, but we wanted to find y of 3. So let's plug in a 3. And that's it. That's our final answer. Ln of 3 is approximately equal to this value right here. Okay, the real value for ln of 3 is 1.098. The approximation that we got is 1.103. Now those two values look like they're way off, but I want you to pay attention to those last 3 numbers. This is kind of like 103, and this is kind of like 98. Those numbers are actually pretty close. This is not a bad estimate. Okay, we're doing last example. It's number 6 of 6. The reason why you see this number 7 here is because this example goes with question number 7 from your homework. And actually, this example here is just meant to explain the problem that we just finished. The example that they just gave us was evaluating ln of x plus 1 when x is 2. We changed it to just an ln of x when x is 3. You can see, hopefully, that that's the exact same problem. It's just shifted right 1. So this example is just meant to explain that it really was the same problem. It's just shifted right 1.